Okay, now let us switch gears and consider quantum LDPC codes. So what are quantum LDPC codes? Okay, first, suppose we have some parity check matrix. And this parity check matrix, it acts on the space of bits, yes, and it produces some syndromes. And this is one of the possible ways how we can define the code. So we define the code as a kernel. So we can see the kernel of H, yes? Another way to define the linear code is to consider what is called generator matrix. So for generator matrix, we also have some matrix, G. So here I consider the transposed G, and I apply this transposed G to the key-dimensional space, and so I choose the basis of my linear code, and linear combinations of this gives you every possible code word. So this is another way to describe code, and in this way, so we can describe it as an image of G transpose, where G is what is usually called a generator matrix. And now, what if we combine this? Yes, so we get the following object. We have a sequence of maps. And this sequence of maps, it has the following property, of course. Since every element generated from this is a code word, though, it should satisfy this parity check matrix. Then, which means that we have that image of G transposed is a subset. In fact, it's equal, yes, but I'll write it in this way, of the kernel of H. And in fact, you can also write it in a different way. Let me just, for the moment, write equal sign. And you can also write it in a different way. So you can write it in this way. Yes, when we apply first this linear operator, then this linear operator, then we get 0, because we have every code word satisfy all the checks. It means that we have all 0. Okay, and what I described is usually called, so this is called length 1 chain complex. This also called length 1 chain complex. It involves just one linear matrix, and this is called length 2 chain complex. And so what's the general definition? So let us consider the case. So let us still consider the case of chain 2 of length 2 complexes. So, but here we consider a little bit more general situation when we have, so let us call this MZ. This is too high. Okay, F MZ. And HX F M X. Okay. And now we consider more general situation. So we have two matrices, two binary matrices, and they have a similar properties. So here we have, so we require that H X multiplied by transposed HZ equal to 0. And equivalently, so we can, of course, write it this way. But now we can see the more general situation where it is not required that this is a generator matrix. So it can be generator matrix for a small code. And this more general situation, this is exactly what is called a quantum CSS code. CSS code. Calderbank, Steen, Shor. And why these quantum codes are important? They are important because there are a lot of evidence, both theoretical and practical, that you can use such codes to construct fault-tolerant quantum computers. And fault-tolerant quantum computers, of course, are interesting. So I hope you've heard about this. So this is not my topic today, so I'm not going to describe why quantum algorithms are interesting. So for me, it's just a very interesting theoretical problem, how to construct quantum codes, because it's somehow related also how we construct classical codes. Okay, but let me define more formally what do I mean just by this quantum code. So this quantum code, it is defined by two matrices, HX and HZ. And we interpret, so what are the code words? Yes, why do I call this object a code? What are the code words? And the good way to interpret this as a code is to consider the quotient space. So let us consider the quotient space. So we have some small code generated by this matrix, and we have some code that checked by this matrix, and it contains it, yes? And so this quotient is called, this is exactly what we will refer to as code, yes? And how we interpret it, so in the standard picture, we have a set of bit strings, so we have a Hamming space, yes? We have Fn, and we have a standard Hamming distance between bit strings. But here we have a little bit different situation where we have cosets. Yes, the elements of this are cosets. And what is the natural distance between the cosets? Huh? Sorry? It's just the distance between different sets, the smallest distance between the, so yes, by definition, the distance between two cosets is just the minimum distance between different elements of these cosets. And this is exactly what we will call the X distance. So the X distance, and in fact, you can easily check that this is exactly the same as a minimum weight, since we are working here with linear, with vector spaces. Yes, you can easily check that this is exactly the same as X from CX, which is not from C, sorry, let me correct this. So this is X from kernel HX, which is not from image HZ. So this is exactly the same as the minimum distance between different cosets. And the proof is almost the same as for classical, standard classical codes. But what is interesting that, so we can also, and what makes this idea of quantum code is really fascinating is that you can also, you have some dual picture, interesting dual picture. You can also consider transposes of these matrices. And you get exactly the same. Why we have exactly the same? So we get exactly the same property because I can transpose this condition. And when I transpose this condition, what I get Hz, Hx transpose equal to 0. So we still have the same kind of property, yes, but in a different direction, which is really interesting. So, and if we denote, use some notation, if we denote by kernel Hx Cx and kernel of Hz Cz, then we see that so we can also consider kernel Hz divided by kernel by image Hx transposed. And so we also have some interesting observation that this guy, what is this guy? What is the kernel of Hz? So Hz was a generator here, yes? And so here it's a kernel. So so this is the same as, so if in this notation that I introduced, so we can also put it in this way. So it's Cx divided by Cz dual. This is a dual code. Yes. And here we also have Cz divided by Cx. And also Cx is dual. Because image of Hx, yes, it's, so here Hx works as generator matrix. And here Hz works as generator matrix. This is why it is dual. Is it clear? Do you have any questions? So, okay. It's a quotient Hamming distance, yes. And yes, and the reason why I introduced this dual picture, because in quantum world, so I'm not going to describe it in full detail, but in quantum world, so we also, we have two types of errors. So we have standard bit flips, and dx just corresponds exactly to this. But we also have another type of error, which is dual in the sense, like in the sense of Fourier transform. So we have this space, yes, it's a abelian group, and we have its Fourier transform, which is called Hadamard transform. And in this sense, we have a different group, yes, dual abelian group, and this group, so this it corresponds to what is so-called phase flips. So we have two types of errors, and I don't have enough time to describe this in more detail because this is usually takes I don't know, just to describe this quantum interpretation, just 1 or 2 lectures, and so it's quite hard. So I hope you have some intuition. But here, so my point is that we also are interested in a different distance, which is defined in exactly the same way, but we change h and z. Here hz minus image hx. So we have a completely reverse situation here. And what is the minimum distance of the quantum code? It's a minimum of these two. Yes, because we want to correct both X bit, standard bit flips and phase bit flips. Okay, so this is so we define minimum distance, and what is the? I also forgot to mention the dimension. So what do you think is the dimension of the code? How would you define it? It's a dimension of the code. So again, so and in fact, it is the same. Yes, it is the same, and this is the first fact that we can check. Yes. So this dimension is exactly the same. So we can define as either it's a dimension. So K is dimension of this space, but this happens to be the same as the dimension of this space. And in fact, the way to see it is the following. So you can just derive, so what's the dimension of this space? So we have n minus, so what's the dimension of this? N minus rank of the matrix HX. But here we have also space generated by the rows of the matrix HG. Then we need to subtract also this one. And if you calculate the dimension of this guy, it is exactly the same. Yes? So we can use this as our definition of the dimension. And now we completely define our object, yes? So our CSS code defined by two parity check matrices, and it has the following parameters. And we usually denote it like that. And one side note why, how it is related with quantum. So in the real situation in quantum computer, our code words, so here I said that the code word is a set of bit strings. So in quantum world, it corresponds to a superposition of the bit strings. So our code word is a superposition, so it's a sum, yes, of these bit strings, which means that if we try to measure this register, so we get one of these elements uniformly at random. And this explains why we have this kind of definition of the minimum distance, because now, what if I apply element of this guy, yes, of this space? The elements of this space are called degenerate code words. So we have standard code words that satisfy this equation, but we have also degenerate code words that are generated by this guy. And what if I apply the element generated from the image, to one of the bit strings? What happens with probability distribution? It is exactly the same, because this is a coset. So we have exactly the same superposition, which means that some code words, so unlike as for classical codes, when we apply some bit string to our register, so we always change the state. But in quantum case, yes, since it's a superposition, when we apply some bit strings, they do not harm, they do not change the state, so, which means that we should ignore them, yes? So we should ignore them, and we should consider code modular, these degenerate code words. Okay, let me give an example of maybe the simplest, one of the simplest quantum codes. Let us just consider very familiar code. I guess everyone knows what it is. Okay, so let's take HX and HZ, parity check matrix of a Hamming code. And surprisingly, so we can use it, and we can check that it satisfies our definition. But I should warn you that we cannot use just arbitrary parity check matrix. This is one of the main problems with quantum codes. Yes, they should satisfy this condition. And you can check that indeed, so by the way, what this condition means also? It means that every row of the HX is orthogonal to every row of the HZ. This is exactly this condition. And you can check yourself that Hamming code has this property. And in fact, many other codes, for example, Reed-Muller codes, also has this property. It's not so hard to prove it. And we can use them to construct also quantum codes. And what are the parameters of this particular code? So this is a, so the n is equal to 7, so it's clear. What is k? What is k? Sorry? No, 3. No. 1. Yes, because it's 7 minus. So here we have, so here we have two parity check matrices. And each row from parity check matrix decreases the dimension, yes? So we have, so the dimension, so another way to put the dimension is just n minus the number of linear independent x checks and linear independent z checks. So we have 7 minus 2 by 3, and this equal to 1, yes? And what about the distance? And anyone guess? Yes, it's 3, yes. It's 3, and so first of all, Hamming code has distance 3, and you can easily check that some, for example, these code words, you cannot generate it. So how you should check that this is indeed a code word? So you need to find a code word of a Hamming code that cannot be generated as a by linear combination of parity checks. But since all these checks have even weight, yes, when you have linear combinations of this, you also get a vector of even weight. But this is a vector of not of even weight. So you cannot generate it. So this is indeed from CX, but not from CZ orthogonal, yes? And hence we prove that this is a code with such parameters. Okay, I think now it's more or less clear, yes, how we define a quantum code and how we define the parameters. Now the question is, so in the quantum case, so in classical case, how we usually do the decoding? So we calculate syndromes, yes? First of all, usually calculate the syndromes and look at them. And we do the same in quantum case, but how we calculate the syndromes? We do the measurements with the qubits. And when we do the measurements with the qubits, we interact with the qubits and we change them. And this is the main problem in the quantum case, which means that in quantum case, we need to use quantum LDPC codes because we need very small local checks. So we interact with a small number of qubits as possible. And so quantum LDPC code, QLDPC code, is a code where HX and HZ are sparse. Okay. And what is the problem with designing? In fact, you can easily show that there exist good CSS codes just by using some kind of Gilbert-Farsham bound. So you can just generate a random linear code, and the random is subspace. So so another way to define CSS code is just you just need two codes, code and its subcode. And you can choose randomly C and choose randomly its subcode. And this, you can prove that this, in fact, give you code with good parameters. And it's not very hard to check this. But the problem with quantum LDPC codes, because this kind of random ideas doesn't work completely. And what is the problem here? Okay, let us choose this matrix randomly. Then we have a good code, yes? This high probability. But here we have a problem, since every row of HZ is a code word of HX. And we have a problem, so this matrix cannot be sparse. So its rows should have a lot of ones, yes? Because if we put this randomly, then we cannot use sparse matrix here. And also in the different direction, so which means that this standard type of random construction completely fails here. Yes, you need some way, some clever way to generate HX and HZ simultaneously. So you need to devise some very weird distribution of these matrices, yes, to produce good codes. And this is one of the main problems why this problem is so hard. And what people usually do, they found that this thing is related to a chain. Sorry. Okay, so what people usually do, so they notice that this thing is very similar to what in algebraic topology we can see. Yes, this is what is called a chain complex. And chain complexes, there are a lot of them. If you open any book on algebraic topology, you can find a lot of these guys there. Yes, and the first approach was, and currently this is the best approach, is just to take any topological space and try to construct some chain complex out of this topological space. And okay, I will describe it later. So what's your question?
CSS codes are basically which are each contained in the dual of the other. Each of these classical codes might have a classical distance dx and dz tilde.
Yeah.
The distance of the quantum CSS code is not the distance between the code words, but distance between the portion spaces, which could be a quantity larger than.
Yeah, that's exactly the point. Yes.
In this particular example, it so happens the classical distance itself is.
Yeah. It may happen, but it may not happen. Yeah. Okay. Yeah. And yeah.
Actually have code words with bad distance.
Yeah.
But when you put them together, the quantum code has actually good distance.
Yes, that's exactly the case with quantum LDPC codes, because this one is not LDPC, so it's a dense code. But for LDPC codes, we always have this situation that you mentioned. Yes, because our matrices are sparse, so which means that we cannot have large distance of a code defined by HZ. Yes, so this is exactly what I noticed. So this is a really weird situation. Yes, so we need to find some code that has very small distance, constant distance. But then you can find some subcode that generates exactly all low weight code words. Yeah, this is not a very easy task. And the solution is topology, algebraic topology. And let me describe a very famous example by Kitaev, what is called Kitaev toric code. So the idea is the following. You define, so in topology, you have this notion of chain complex that I already mentioned, that, for example, if you consider this graph, you have some edges and you have some vertices. And let us consider the linear combinations, formal linear combinations of edges. And let us also consider formal linear combinations of vertices. And we can define a map in a graph, which we denote by delta, partial. And it is defined as the following way. So it's the elements of this space are formal linear combinations of edges. So I just denoted it in this way, but I consider the elements of this like, I don't know, if we have E1, E2, E3, so like E1 plus E2. So this is, so we can also consider this as a vector, yes, indexed by elements. And here, so this vector is like this. And I just denoted. So this is standard way how you describe these linear combinations. And now you can define this map. So you define it on each edge as, so here F is a field of two elements. So let us suppose we have a vertex VV prime, so we define it V plus V prime. And then extend it by linearity. And here we have some linear map. But what we can also do, we can also consider what Max described in previous lectures, what is called simplicial complex. Yes, so we can add to this graph some simplices. For example, this one, triangles. And you can also consider, not for every three vertices, so for some of three vertices, we add triangles, yes? So we have also a space of triangles. And we can also define for a triangle that consists, for example, from these three edges. So we can define it like so it's just the sum of the boundary. That is, for this reason, it is called a boundary map. And now let us consider the kernel of this map. What is the kernel of this map? F is, so it's always F2. Yeah, that's important, yes. Here, and so in my today's slides, it is F2, or at least it is have characteristic 2, so that's important. Okay, so what's the kernel of this delta? So this is delta, not gamma. This one. Okay, let me just do, so this is delta 1. So what's the kernel of delta 1? Yes, this is exactly the cycles. So this condition, yes, that we have, so we put bits here, and here we have some kind of Tanner code. Yes, we have checks on each vertex, and it checks, it's just simple parity check. And we have 0, yes, so the kernel is a cycle. This is even called cycle code. And by the way, this cycle code, what do you think, what is the largest minimum distance we can usually have if we, for example, use some sparse graph? Usually it's not very high, so it's like logarithm, because it's, so what's the minimum distance for a graph? What's the minimum distance of this graph in general? It's the size of the smallest cycle. And this is what is called in graph theory girth, yes? And the girth, we know that it's usually grows for example, for expanders, for its growth like logarithm. So as a code, it's not very interesting code, unfortunately. Okay, but here we have another map, yes? And we can check that if we apply 2 times, then we to this, then we get 0. You can easily check this because it's, so each vertex participates 2 times. Yes, it's sum of this. And when we apply to this, so we have each vertex participate in the sum 2 times. So we have 0. So this guy has this property. And this is one of the key ideas behind topological quantum calls, yes? Because we can do this not only with simplicial complex, so we can consider any weird topological space you want. We can do what we can do. We can just divide it, maybe on triangles, maybe not only on triangles. We can also use squares, and you can easily check that for squares and for other shapes, we have the same property. Yes, so we can divide it in some cells, what is called cells. And we can define, okay, let me assume that it's just like such kind of cell. And we define, this is called a cellulation in algebraic topology. And then we can define this chain complex. And this chain complex, it gives you an example of a code. And such, okay. Yeah, because because boundary of each triangle is a cycle. Yes, and this exactly, yes, it also explains the standard terminology here. So because the image of this map, it is what is usually called boundaries. Yes, because it's the boundaries of these triangles or other shapes. Yes, but each boundary is a cycle, as you can see, and hence it satisfies this parity check. And we have exactly the same situation as before, as for quantum codes. And this is a key idea behind topological codes. And the first example of such topological codes is a Kitaev toric code. So it's so we just have a torus. Sorry, not very good torus. Okay, this is maybe the best I can draw a torus. Okay, I'm not a geometer. Usually geometer can draw a torus in a much better way. So let me also draw it in a different way. So we have a torus, and we divide this torus into squares. So here we have L edges, and here we have also L edges. So, and we consider this chain complex. We have squares, we have edges, and we have vertices. And as before, yes, so we have the standard boundary maps. Okay, let us calculate the parameters of this code. What is the length? So this is a quantum code, yes, and the length is the number of edges. What's the number of edges here? Okay, this 2L squared. Let us calculate. Let us calculate the distance. First, the distance. What is the distance? Okay, what are degenerate code words here? The degenerate code words are boundaries, yes? So for example, I can take some squares and sum their boundaries, and I get, okay, and here I have some boundary. And all such elements, such boundaries, yes, are degenerate code words from our subset. And as usual, the standard cycles are our code words. So, and what is the distance? The distance equal to the minimum weight of the code word that cannot be obtained as a boundary. And what's the value? And It is L, yes, exactly. And here is an example of such. For example, this one, yes? And in picture, you can also represent it like this. And you also have another example, yes? This one. And in pictures, it corresponds to this one. Okay? Okay, degenerate code words are the code words in the, so a quantum code is a pair of nested codes. So the small one is a degenerate. So we call it degenerate because we do not consider them as harmful, yes, as I previously said. So, and here degenerate code words are boundaries. So, yeah, this is what I call boundaries. And cycles are our standard code words, and boundaries are our degenerate code words that we, and our code word is a quotient of all code words modular degenerate code words. And here, so the distance is equal to L. And it is not a formal proof, okay? It's not a completely formal proof, just, okay. Sorry? Oh, okay. That's exactly correct. So let's put it like this: dx, yes, exactly. And it's interesting that what is dz here? Let us calculate the number of squares and the number of vertices. What the number of vertices is L squared. The number of squares is also L squared. And we can see that we have a very symmetric picture, which suggests that maybe dz is equal to dl. And this is in fact true. And in order to see that, so you can just consider, so now we should consider our squares as vertices, our edges again as edges, and our vertices as squares. How we can do this? And this is a very standard idea in algebraic topology. It works for closed manifolds, and so torus is a closed manifold, and for some maybe other spaces. So you just consider. So so we can consider new torus. So these are my vertices, and we connect two vertices by edge if two squares are connected by common edge, yes? And now if you consider the reverse parity check matrix, you will see that this will correspond exactly to the same toric code, to the same torus, yes? But here each square is converted to its center. So it's now treated as a vertex. Edge is we connect by edges to adjacent squares, yes? And we have a square if we have 4 adjacent squares. So in fact, this is also equal to L. And the last parameter is a little bit harder. So you can do this just by linear algebra. Just if you just write down this parity check matrix, for example, calculate their ranks. So you can prove that the dimension of this code is equal to 2. And exactly, and since so the standard interpretation, yes, of the dimension is the dimension of the quotient space, and we have two linearly independent representative of this quotient space. So this vertical and horizontal lines, yes, and their linear combinations gives you this two-dimensional space. Okay. And this, in fact, this code is just an example of a very large collection of codes. So, and what people try to do after this, so they try to construct some weird topological spaces, yes, like I showed here. So You can easily, from using tools from algebraic topology, show that the dimension roughly corresponds to the number of holes in the topological space. Number of holes. But the distance is also very interesting. As you can see, the distance corresponds to some loops that cannot be contracted. Yes, so we have a loop that goes through the hole. And so the minimum distance is a loops through the holes. Yes, the loops that cannot be contracted to the point. And so this was also studied by topologists long before quantum codes. This is what is called a systole. And this is the reason why it is called a systolic distance. So this dx and dz distance is usually also referred as systolic distance. And here we have a problem. Yes, we need to find some weird topological space with a lot of holes, but with large systolic distance, the size of the systole. And we can see that they contradict to each other. Yes, the more holes we have, the less systole we have. So this is a like topological interpretation of this problem. And the solution came quite unexpectedly from coding theory. Yes, so was not related directly from topology, and there is a very nice construction called hypergraph product codes, which is not very geometrical, I would say. Yes, so it's more like coding theoretic construction, but it at least solves the problem. At least it allows us to construct spaces with a lot of holes, yes, with a large dimension. So here as you can see, so the parameters were the following. So it's like n2, and then like square root of, okay, let me put it this way. So we can see that the distance is not very large, so it's just a square root of the length of the code, but the dimension is awful. It's very awful. And hypergraph product code construction solves this problem. And I think maybe, so okay, at least I can start to describe it, but maybe we can also analyze it more thoroughly next time. Okay, let me briefly describe it. So first of all, let me remind what is called a tensor product code. Tensor product code. So tensor product code is a set of matrices. So we have two codes. A tensor product code is a set of matrices such that every column is from code A, and every row is from code B. Yeah. So here, this one is from code A, and this one from code B. How we can check this? What are the parity checks? Yes, we can consider this matrix, and we can consider the following checks. We can multiply this W by A, and this checks this condition. Yes, because so W is a matrix. So say NA by NB. And this equation checks this condition, yes? Because we apply linear operator A to each row, and if it's zero, so we have a zero syndrome. Now, we can also check, we also need to check this condition. And here we can multiply by B transpose, because yes, we need to apply operator, and here I forgot to say, so, okay, let us assume that code A and code B defined by corresponding parity check matrices. Okay. We can, another type of syndromes, yes, we apply this linear map. And we have another type of syndromes. But as you probably know from the previous lectures, that maybe you've heard someone, so that tensor product codes has a lot of dependencies. Yes, and when especially this is very important in the context of locally testable codes. Yes, you know that for local testability, we need a lot of dependencies in the syndromes. And you can easily check that this tensor product code has a lot of dependencies. And let me show. So let this syndrome is equal to U, this syndrome equal to V. Then what we can do? We can multiply this guy by B transpose, and this guy by A. And what we see? We see that A multiplied by V multiplied by B transposed is equal to A to U multiplied by A, where V and U are syndromes. Yes, our syndromes. U is equal to W B transposed, and V is equal to A multiplied by W. Yes, this is our syndromes. And if you substitute, what we have? We have A W A WB. Okay. You can easily check that this, in fact, true. So we have dependencies between U and V. And the number of dependencies is precisely the size of this set. So this is, let us denote it by S. Okay. And now what is a hypergraph product code? Yes. So now we consider a chain complex out of this. Construct a chain complex. And we define a hypergraph product code defined by these two matrices, A and B, as a quotient that corresponds to this intermediate level. So it's so we have syndromes that should satisfy this condition. So we have pairs of syndromes that should satisfy. And we divide it. So this is our cycles. Yes. Cycles. These are syndromes that satisfy this condition. And our boundaries, these are all possible syndromes. Yes. So here it's okay. And if you need a chain complex, directly see this chain complex, then it is the following. So it's FNA by NB. Here we have F, what's the parameters here? So we assume that this is a MA by NA matrix, as this is MB by NB matrix. And here we have, yes, so this is NA, this is NB, this is MA, and this is MB. So this is MA by MB plus MB plus multiplied by MA. And here we have MA by MB. And our maps are the following. Yes, so V goes to V B transposed A V transposed. And here U and V goes to, we need to satisfy, we need to check this condition. So it's V B transposed minus A U. Yes? So here our check equation. So here I formally define you some linear maps, two linear maps that satisfy this property. Yes, and you can see that if you substitute this into this, yes, you can have zero because we have this relation. And this is, in fact, a valid quantum code. But maybe next time we'll describe its parameters. So so now I can say that if the only thing that I want to say, that if we use such matrix in this construction, where H is a full rank matrix that define a code with distance kernel H, yes, then we would have a code with the parameters n squared plus m squared. Here we have squared and the distance d. Okay. And an exercise to you show that toric code is a special case of this construction. Just think about it. Yes? Just find exercise. Yes? Find H for toric code. Okay. Okay, do you have any questions or? So it is shown here, maybe it's too high. So it's A has, so matrix A has the parameters MA by NA. So it's a linear operator that takes vector of length NA, it converts it to vector MA. And the same for here. Yeah. And each column, I apply exactly the same matrix A. And here, so in matrix operations, it can be quite easily described like a matrix multiplication. Yes, it's very handy here. Okay. Any other questions? H transposed, this is because of the dimension. If you calculate, so what I described to you, I do not prove that this set is larger than this set. But you can easily see this if you choose the parameters like this. Yes, so the dimension is very simple because here you have, so here you have n here you have M, but here you have M, and here you have N. And so this means that here we have M by, so M by N and M by N. Yes, but here we have M squared and N squared. And so what's the formula for dimension? The number of bits here minus the number of bits here and the number of bits here. And if I choose it in this way, I can ensure that this size is larger than the sum of these sizes. Yes? Is it clear? So, but of course you need to calculate carefully, yes, to show that the dimension is k squared. In fact, it's quite easy. So maybe I will start from this next time, and I will do all the calculations because it's, I think, interesting. Okay.